All right, today is one of the last topics we're going to cover with Taylor series and power series. And it is called the Lagrange error bound. It's not LaGrange, it's Lagrange. Because the man whose name it comes from was what nationality do you think? French. He was French. Monsieur Lagrange was French. And we're talking about errors with Taylor polynomial estimates. Okay? Now, we've talked about errors before. Okay? We talked about alternating series errors. So if I have an alternating series that goes out to the fourth derivative, what's the error term? The fifth term, right? So it's always the next one in sequence. That's only, though, for alternating series. What about everything else? How do you know how good your estimate is if you go out a certain number of terms? How close you are is very important in many different fields. If you cannot be off by a certain amount, or that part may not fit into that component. Or when your spacecraft is coming in for a landing, if it's off by too much, it's not going to go through the atmosphere, it's going to bounce off the atmosphere. So there's very important applications to error. So we're going to spend today talking about how to calculate error for non-alternating series. And that is using Lagrange's error bound. So before we do, we're going to talk about some vocabulary that a very good friend of mine, Mr. Paul Forrester from Alamo Heights High School in San Antonio, came up with. Now, this man, I got to tell you, he is basically my role model for teaching. This man is now in his 80s. He retired from this high school after teaching for 50 years. Can you imagine doing the same job for 50 years? That's a long time. But he is an amazing teacher. He has written many calculus books that calculus teachers use in the classroom today. He's written calculus books, pre-cal books, algebra 2 books. He's just amazing. And he knows how to explain things well. Okay? So let's talk about the vocabulary that he came up with to help this make a little bit more sense. First thing, this is some of this vocabulary we've been using all along. A partial sum is the sum of the first few terms of a power series. I kind of skipped over this. F of x is a power series. Okay, so you have some general power series that goes to infinity. A partial sum is the sum of the first few terms, however many say, 4, 5, 6, whatever. The tail, this is his words, is the rest of the terms of the series after the partial sum. So when you write out a series, you have blah, 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 and you stop. First term, second term, third term, fourth term. Everything after that, this is the tail. Okay? This is the partial sum. It tells you, you decide where to stop. Okay? The remainder is the number you get by adding all the terms up in the tail. So if you take all of these and add them together, that's your remainder. Are you following what I'm saying? Okay. So take a look at this. Does it make sense that the series is equal to the partial sum plus the remainder? That's the whole series. Where you choose to stop plus everything you didn't choose to use. All right? The error is the error you make by assuming that the answer is just the partial sum part. If you choose to stop right there, you're not going to have the true answer. You're going to have an estimate. And the error is the error you make by saying, oh, that's the answer. No, it's not the answer because you left off all of this. Okay? So the error is the same number as the remainder. Does that make sense? Yeah. The error is what I didn't talk about. I said the answer was this. The answer is really all of this. So the remainder is what the error is, what I forgot about, what I didn't use. The error bound, and this is a word that you need to be familiar with. The error bound is a specific number known to be greater than the absolute value of the remainder. Now, that's kind of confusing. What I'm saying is, because this remainder part is infinite, there is no way I can add them all up. I can't. But I can find an estimate that I know is going to be bigger than the absolute value of all those numbers. And that's called the error bound. And that's what we're going to find. I think in some fields of study they call it a tolerance. It's just how much off you can be, okay? For the alternating series that meets the 3 convergence hypothesis, now we just talked about that. In order for an alternating series to converge, it has to alternate, it has to go to 0, and all the terms have to get smaller. Those are the 3 things. We just talked about that on the previous thing that we were doing. The absolute value of the first term of the tail is the error bound. And we talked about that as well. If you go out 5 terms, the 6th term is your error bound. Now, the next part talks about what's called the Lagrange remainder. And I'm going to go ahead and read it with you because it is a little confusing. And one thing you need to understand about math, college level math, is sometimes math has to be read very differently than English. When you read a novel, do you usually have to reread the same paragraph over and over again? Or can you just keep going pretty much straight through it? You can pretty much go through it. Science textbooks, sometimes you have to go back and read it again because you might have missed a word. Oh, I didn't get that. Math, on the other hand, you may have to read the same paragraph 5, 6, 7 times until it sinks in. And some of you may have already experienced that. This is just the way math works for people who do well in math as well as people who struggle with math. It's true for everybody. So let's look at this and let's just go very slowly, see if we can figure out what's going on. Now consider what Monsieur Lagrange is credited with showing. The Lagrange remainder, which is the error, is exactly equal to the first term of the tail. So it's kind of like the alternating. But instead of evaluating the derivative at c, like we've been doing with alternatings, which is instead of evaluating at c, which is the number where we expand our series, that's the number we put in the parentheses with x every time, it is equal to the derivative evaluated at some other number z, which is between c and the value of x at which you're evaluating the function. That's as far as I want to go. Okay? What makes this weird is bringing in this z. We've talked about c this whole unit. We've talked about x since elementary school in Algebra 1, but we've never talked about this z thing. Okay? What it is we're going to find a number that we know is the definite maximum that the error can be. We can't find the exact error, but we can say, okay, well, it's definitely going to not be any bigger than this. All right? So, in the next box down here, it has what's called Taylor's theorem. Take a look at this top line right there. Just look at it very carefully and read through the function. Does that look familiar? Have we seen that equation before? It's a Taylor series. It's missing the 1 factorial right here, and it's missing the 0 factorial right there. But other than that, that's just a Taylor series, right? Okay. But then they put on this Rn of x. That's the tail. So that's basically saying everything else. Instead of writing plus dot 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 plus the nth term, they're just lumping it all together and calling it R. This is the remainder. That's what's left over that I didn't add together. And then over here in this box here, or it's still in the box, is another definition of what the remainder is. First time I saw that, I went, what in the heck is that? That's pretty yucky looking. But we're going to change it and make it a little more simple because I found a different way to explain this that I think is going to make it better. Actually, we're looking more at this one at the bottom. We aren't going to worry about the error. We're concerned more with the error bound. We're going to rewrite this one here this way. I want you to write absolute value of Rn of x is less than or equal to. This right here is the error bound. So anytime a question asks you for an error bound, you're going to use this formula I'm about to give you. Okay? Now, it is equal to the absolute value of capital M over n plus 1 factorial times x minus c to the n plus 1. Just write that down for a minute. Capital M to the n plus 1 factorial. capital M over n plus 1 factorial x minus c to the n plus 1 power. Okay. Now, I'm going to come up here. I want you to look at the screen. I'm going to cover up that r. All right. Notice the denominator from here to here. It's just one more. Agreed? The power on x minus c. It's just one more. Agreed? Okay. What's changed is the top. The top is now just this m. All right? If I was to do the next term, I would take the next derivative and I would plug in a c. But because we're now dealing with a non-alternating series, m is slightly different. This is how m is defined. M is the absolute value of the f of n plus 1 derivative evaluated at z. Okay? Now, what is z? I still haven't told you what z is. I'm going to define z in a certain way that I found to make things really easy. Z is a number between x and c. Okay? Z is between c and x, somewhere between c and x. C, we know where c is. We've seen c before. It's the one in the parentheses with x all the time. And x is the number where we want to find the error. They will tell us x. Okay? And how do you find z? I'm going to have to squeeze it down in here. To find z, here's what you do. You plug in c to that function right there. Then you plug in x to that function right there and choose the biggest answer. Or this is how you find, I need to rephrase how I do this. You're not finding z with that, you're finding m. Okay, let me change that because it's really finding m. I just realized that. You plug in the c, you plug in the x, because it really doesn't matter what z is. We just care, we want the biggest number. I want you to come back up here. Someplace where you have an m, please put an arrow to it. We're going to call this the magic max, because it is the maximum answer. That's why I'm saying plug in c, plug in x, pick the biggest. We want the maximum. Okay. We aren't going to be doing much with this today. That's going to come more on Monday. But I wanted to introduce it to you because it's a whole part of setting this up. Okay. M has to be the maximum that it can be. So we plug in the c value, we plug in the x value, see who's bigger. That's our answer. All right. I'm not going to worry about what's left on the bottom of this page. I want to go to the back. All right. I'm going to tell you that AP very much lets you know when to use this. They will either say error bound or Lagrange error bound, and that's your cue that you got to use this formula. Okay, there's no think about it. Oh, do I need error bound for this? No, they're going to tell you. They're going to say error bound. Okay? Now, one other thing I want to tell you is you're going to see a lot of times something that looks like this. You'll see an absolute value of a p of something minus an f of something, and then it's less than a number. Okay? When you take your estimate and you subtract it from the original equation, that is your error. We did that a few days ago. So anytime you see this notation, just remember that's your error. And we'll come back to that in a minute because we're going to see it in a problem. The function f has derivatives for all orders. In other words, it's got a first, second, third, fourth, fifth derivatives. You're good. Assume that f of 2 is 6, f prime of 2 is 4. Doesn't this kind of look like your quiz? Yeah. Didn't your quiz start like this? Yeah. Now it says, instead of doing what you did on the quiz, write the third degree Taylor polynomial for x about 2. And then use it to approximate f of 2.3. All right, give 3 decimal places. Here we go. P3 of x. When you do a Taylor polynomial, you call it P for polynomial, and you put at the bottom what degree they asked for. This asked for a third degree, so we put P of 3. All right, do you remember how this starts? Yes. What do you do first? What's your first fraction? It's going to be 6 on top.
6 over 0.
0 factorial. Now this one has a about 2.
X minus 2.
X minus 2 to the what power? 0. Plus. What goes next? 4 over 1 factorial. X minus 2 to the 1. Plus. Can you keep going? Yeah. Let's just keep going. Negative 7 over 2 factorial. X minus 2 squared. Plus 8 over 3 factorial. X minus 2 to the third. Okay. You have just built a Taylor polynomial. This is what we did the first week of this unit. And you've been using it all along. Okay? The only difference about this compared to the series, we stopped. We didn't go plus dot 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 plus something else. Okay? Let's go ahead and clean it up since we need to plug a number into it. What is the first term going to clean up to be? That's 6. Plus 4x minus 2. Do not distribute. It's going to make life easier if you don't. Plus negative 7 over 2, x minus 2 squared, plus 8 over 6, which is 4 over 3, x minus 2 to the third. Okay? Did it. If you can do that much, you've already got points on this 9-point free response question. Can you do that? Okay. Now, we need to use it, i.e. that formula, to approximate f of 2.3. But before we start plugging it in, let's take a look at all the parentheses. If we plug in 2.3 to all the parentheses, what are we going to get? 0.3. So let's just write it that way. 6 plus 4 times 0.3 minus 7 halves 0.3. I always like to put a 0 in front of my decimals just because I don't forget the decimal, or I'm less likely to miss it. 4/3 0.3. As soon as you're done writing, grab your calculator and type that in and see what you get. Question?
What's the thing? You forgot the approximation thing. You made it.
I sure did.
What's it called? Like, don't the other ones go up to a power?
Do they?
Yes.
Yes, they do. Good catch. Very good. 2 brownie points for you. For my approximately equal to squared third power. Excuse me. So I'm going to scoot that up so I have room to put my calculator underneath it, and you can hopefully see what's on my screen as well as what I'm typing. So we have 6 plus 4 parentheses 0.3 minus 3.5 0.3 squared plus 4/3 times 0.3 to the third. And we get this, which is 6.921. Said 3 decimal places, gave me 3 decimal places. We're good. Let's turn that lamp off. I have to turn the lamp on to see the calculator screen, but then if I leave it on, it makes a glare on the iPad screen. All right. So far, we finished part A. We created the polynomial. We wrote down what the approximation is. So, f of 2.3 is an estimate for this value. Now, look at the next question. And this one actually, it's a scary looking question, but oh my gosh, if you can interpret it, it's very easy to do. The fourth derivative of f, which is the derivative past the one where I stopped, satisfies this inequality for all x in the closed interval from 2 to 2.3. Does this look like the formula that I gave you on the previous page? Turn back and look if you don't remember. Part of the formula.
What, the RN one?
Look over here at the stuff we wrote at the bottom. It says the fourth derivative of x.
Yeah.
Which part am I talking about it looks like? Is it the whole Rn equation or is it the m equation?
It's the RN. Bigger.
Okay. Over here, it doesn't say anything about a derivative, does it? Okay, but this m says f of n plus 1, which is like a derivative at a point z.
Yeah.
So that expression in the problem is m. So let's go back. This right here, this is m. This is telling me that m is less than or equal to 9. So I don't have to go find m. They're telling me what m is. So now all I have to do is plug the m into that error bound formula and use it. Then it says, use this information to find a bound for the error. Remember I told you they're going to come right out and tell you, use an error bound. If it says error bound, you can either use the alternating series rule or you can use Lagrange. Now, go back to the problem we just wrote out right here. Can you see it? Or am I up too high? I'm up too high. Is this a true alternating sequence? No. It has positive, positive, negative, positive. That's not an alternating, so I can't use alternating. I have to use Lagrange. All right? So what we do is, I'll write it down for you, but this is copying down the formula from the front of the paper. Absolute value of R3 of x, that number is the same as the polynomial. If I built a polynomial P3 of x, because it's a third degree, the remainder is a third degree also. This is less than or equal to the absolute value of m over n plus 1 factorial x minus c to the n plus 1. Now, we're going to change all of these n's and c's to what the numbers actually are for this problem. Okay? So, absolute value, R3 of x is less than or equal to. What did we say that m is less than or equal to? 9. So put a 9 on top. N is 3, because n is how far out I took my polynomial. So what's the denominator going to be? 4 factorial. The factorial beyond the one where I stopped. If you go back up and look at the original problem, we stopped at 3 factorial, so this one is the next one, 4 factorial. Okay? What is c? C is what? 2. So it's x minus 2 to the 4th power. But wait a minute. This is supposed to be a number. I didn't put in a number for x. Did it tell me what x was? X is 2.3. It's the question. Look right here. It says f of 2.3. So that's my x value. So go back. My apologies. I should have caught that beforehand. 2.3 goes there. So it's less than or equal to, let's clean this up a little bit. What is 4 factorial?
24.
24. And the parentheses, 0.3 to the 4th power. Now, you need to put that in the calculator. Let's put it right there. So we're going to put in fraction bar 9 over 24 times 0.3 to the 4th power. Okay, thank you for asking that question. How do you get the absolute value signs? You don't need it. Because of the fact that it's a number, you can just do it in the calculator and go, oh, if I got a negative answer, I'll just make it positive. So don't worry about the absolute value bars. So I get this decimal right here. We're going to take it out 3 decimal places because this is our answer. So now R sub 3 of x is less than or equal to the absolute value of my answer, which is 0.003. I have just found the error bound. The remainder is all of the terms added up, which I, in reality, can't do. What I am finding is the error bound. It is basically, I can't find the exact amount, but it's going to be no more than this many units away from my estimate. Okay? Yes?
So the only time you find it is when it tells you in the problem? Like,
when it tells you error bound, yes, that's the only time you do this.
The R means remainder.
R means remainder. The absolute value of the remainder is going to be less than or equal to 0.003. Okay? So, based on what we did before, you could take the bars off and say that negative 0.003 is less than r, is less than 0.003, right? Yeah. Okay, so what does that tell us? It's going to help us solve C. It says use your answers to parts A and B to find an interval from A to B such that A is less than or equal to f of 2/3 is less than or equal to B. This is called, this is my words, I call this the error window. You are about to construct the error window. And that's basically saying the exact answer is somewhere in this window. I can get close, but I can't find it exactly. Okay? Now, how do you find an error window? You take your estimate minus the error, comma, the estimate plus the error. It's somewhere in between that. The estimate was what we found in part A. What did we find for f of 2.3 in part A? 6.921. That is close to the answer. It's close to that, but I don't know, it's not exact because there were terms after that. What I'm finding now is, well, if it's not exactly that, what's it going to be around? I need to take this and I need to add and subtract this error I just found to give myself a boundary. So my interval will be from A, which is this number, minus 0.003. What's 921 minus 3? 918. So 6.918. 6.924. How did I get that? I took the 6.921 minus 0.003, and then I did 6.921 plus 0.003. Okay? So I now know, because of this error bound, that the exact answer to adding up all those terms in that series forever and ever and ever is going to be somewhere in there.
That's crazy.
That's as close as we can get.
It's also going to be brackets.
It is going to be brackets, yes. Because it's less than or equal to. So it's brackets. Now, the more terms I go out, the smaller the error will be, which means the narrower the window will be. Think about that. If my error was 0.000005, my window would be really, really tiny. Okay, which is even better. Makes it an even better estimate. All right, now, letter D. Could the exact answer be 6.922? Yes. Why? It's in the window. So the answer is yes. 6.922 is in the interval. That's the exact terminology. I like to call it an error window because I think it makes sense.
Yeah.
It's the window in which the true actual answer could be. If you put error window in the AP exam, I think they would probably give you credit for it, but don't quote me on that. What about, could f of 2.3 be 6.927? No, because the highest it will go is 6.924. No, 6.927 is not on the interval.
Is there an official name for an interval?
It's just the interval. Don't call it an interval of convergence because it's not. It's the interval for the error. I know. All right. So that problem was a little bit involved. The more you practice these, the more you're going to see how the problems look, and you'll be ready to do them on the AP exam. All right. Questions? Let's go do the next one. Turn the page. Last one. That was only one example. Now we got to do the second example. Now, I'm going to tell you right now, I'm sorry I did not leave you a whole lot of room to do part A. We're going to have to squish. And if you need to run down the side, that's fine, because B is not going to need that much room. I didn't realize how long A was going to take. Okay, so I'm going to go like this. I'm going to make A go from here, there. That's all the room for A. No, it's not that long. Only if you write big. Okay? Now I'm going to erase that because that's going to bug me. All right. Here we go. Let f be the function given by f of x equals sine of 5x plus pi over 3. Let p of x be the third degree Taylor polynomial about 0. Okay. Find p of x. That means build the polynomial. Can you do that? That's part A from the previous problem. But let's take the derivatives together and make sure we get them right. So underneath f of x, let's do f prime very carefully. What's the derivative of sine? Cosine of 5x plus pi over 3 times 5. Do not forget the times 5. We're doing chain rule. So that's going to be 5 cosine 5x plus pi over 3. I'm putting the 5 in front because it's going to make taking the next derivative easier. That right here is an equal sign. Take that off. Equals. There we go. Double prime. We have to go out triple prime. All right. When you take the derivative of this answer, the 5 just sits there. What's the derivative of cosine again? Negative sine. So negative put in front of the 5. Sine 5x plus pi over 3. I wrote 5 over 3. Times another 5. Negative 25 sine 5x plus pi over 3. Okay? Are we good?
Yeah.
Next one. Triple prime. Last one we got to do. So copy the negative 25. Derivative of sine is cosine 5x plus pi over 3 times another 5. What's 25 times 5? Negative 125 cosine 5x plus pi over 3. Close it. Yes. The negative is right here. I moved it to the front, so the derivative of negative sine is negative cosine. Okay, if I pull the negative out and put it in the front, it can either affect the 25 or the sine. So when I pull it to the 25, now it's really not with the sign anymore, and I treat the sign like a positive sign. And the derivative of positive sign is positive cosine. Okay? Okay? Now, so now we need to build our polynomial. That's why I left some room down here. But I got to do one more thing before I do. I know that the bottom of the first term is going to be 0 factorial, right? And this is P3 of x. What goes on top?
0. Okay, so you have to plug 0 first.
You got to plug 0 into all these answers. So I'm going to draw a line right here. This one I'm going to have to do up here in the sky because there's words in the way. If I plug 0 into this, what is 5 times 0? 0. So ignore the x part. It's just the sine of pi over 3. What's the sine of pi over 3? Sine of pi over 3? Square root of 3 over 2. Okay, now, so we can do these as we go. Now, root 3 over 2, it's a fraction answer. You can put the whole fraction on top, or you can go root 3 and 2 on the bottom. But that's not 20 factorial. It's 2 times 0 factorial. Now, is it an x minus something in the parentheses, or just an x?
Nothing. It's
Just an x to the 0. Plus. Okay, going to be a 1 factorial. Got to go plug in. what's that going to be? 5 times the cosine of pi over 3. 5 halves. So we'll put the 5 on top and the 2 on the bottom, x to the first.
Wait, what are you writing at?
Oh, you can't see out to the side. Thank you. I did that last period. There. Okay. So, let's just go ahead and finish these up. It doesn't matter if you keep going back and forth. I think it would be better just to get them all done. When you plug in 0 to the next one, that'll be negative 25 times the sine of pi over 3, which is negative 25 root 3 over 2. And then the last one's going to be negative 125 cosine of pi over 3, which is negative 125 over 2. Yes, the numbers are ugly. But usually if the numbers are ugly, they don't make you plug anything in like they did on the last one. They just want you to build it. And then we do the next term. Plus, we did the 5 halves. Now it's time to do this one. Negative 25 root 3 over 2. That takes care of that. My factorial is 2. X is a power of 2. Now I'm going to stop for about 30 seconds, and I want you to try to write the third term down correctly. 2 times what factorial? 3 factorial x to the done. That's it. Okay? Did you get it? Okay. If you didn't get it, do you see where you messed up?
I did.
Okay. So, did the first problem. We're done. Now, that's A. Now B. B says use the, oh my goodness, they tell us what to do, Lagrange error. Okay? So, they told us Lagrange error. Now, also, here comes that thing I told you to be on the lookout for. The function, the actual answer minus the estimate is going to equal the what? That's the error. The error is less than 1 over 1200. So we're going to prove that it is. So let's write the Lagrange formula. R little what letter? I mean, what number? R little what? 3 or 4?
3.
3 has to match the P. Good. X, absolute value, less than or equal to. Okay? So I'm going to try to help you memorize this formula. We need to put this on the flip book. What goes on top? M. On the bottom, n plus 1 factorial. And then x minus c, n plus 1. That's the generic formula. Now, if you wanted to go ahead and put in what n is and what c is and what x is, you could go for it. Okay? Let's just leave m until last. So, this is less than or equal to m over what factorial? 4. How do we know it's 4? Because we went out to 3. When we wrote the problem in the previous part, we went out to 3, so it's always the next one. Okay? Now, what is x? It is 1 over 15. Minus, what is c? C is 0. Look at your polynomial you built. Did you have anything in the parentheses with x? No, so it's 0. To the what power? 4th power. Close your bracket. Close your absolute value. Okay, so everything's done except for m. Are we good? Does everybody understand where n came from, where c came from, and where x came from?
Yeah.
Just pull them out of wherever they were.
Where X is,
They will give you an x. Or it will be in the, like in the other one, it was in the previous step. They have to give you an x. All right, so let's go tackle m. M is the absolute value of the which derivative? The 4th derivative, because I've gone out 3 so far. It's always the next one of z. Okay, remember z is an unknown.
Right, but we only have 1 over 15, right?
We have x and we have c.
Yeah.
It's 0 and 1 over 15.
So we have to plug in 0.
Wait till we get there. I've got it. Sine has a nice little trick to it. Okay? So, I need a fourth derivative that I'm supposed to plug something into. So I need to go back and I need to take the fourth derivative of my problem. Here's my third derivative over here. The fourth derivative would be negative 125. What's the derivative of cosine? Negative sine. So that's going to make the 125 turn positive sine 5x plus pi over 3. Is that it? Times 5, which is 625 sine of 5x plus pi over 3. Now, the normal thing we would do next, I'll give you a chance to write that down. The normal thing we would do next is we plug in 0, we plug in 1/15. Now, plugging in 1/15 to that is not going to be pretty, but sine and cosine are very special functions because they by nature have a maximum value. What does a sine wave look like? Draw it in the air. Does the wave thing. Does it have a highest point that it will never go beyond?
Yes.
What is that highest value? 1. So, sine and cosine are unique. Their max is automatically 1. Give you a second to write that down. Very, very important. So if you're given a problem with sine or cosine, you don't have to plug in the x. You don't have to plug in the c. You don't have to see which one is bigger. You can immediately say that the sine part is 1 because that's its max. Always. So that means, and I'm going to scoot this up, so m is going to be the absolute value of 625 times 1. The sine, everything with the sine is 1.
Why do we use the max of it? I was trying to understand why, like, it is.
Because that's the
We can't find the exact number, but we can find a ceiling, a highest value that the number will be.
And that's enough.
And that's our maximum, yes. That's our ceiling that we can find. There's a proof to all of this that's beyond this class, but basically Lagrange allowed us to find it's going to be no bigger than this. That's what we're finding.
Okay.
Okay? So the max is going to be 625, and now I go back and plug 625 in for m. So absolute value of R3 of x is less than or equal to 625 over, what's 4 factorial? 24, 1/15 to the 4th power. Throw that in the calculator. Let's see what's going on here. Now this actually could be done without a calculator, and they may ask you to do that on the AP exam, but I'll talk about that later. 1 over 15 to the 4th power. Now, remember the calculator does not like, the AP exam does not like calculator lingo. Okay? So this is 0.000514. I'm going a lot of decimals. Okay? That's a nice, pretty answer. But it says I'm supposed to show that that is less than 1 over 1200. How in the heck do I know that? Well, what I did when I first did this problem, I said, math, enter, enter. Let's make it a fraction. Oh, my calculator did it this time. Is that less than 1 over 1200?
Yes.
Yes. So, I can go back and erase my decimal. I didn't need it. If you left it, that's okay. 1 over 1944 is less than 1 over 1200, and I am done. did that last period, it wouldn't change it to a decimal. I don't know why.
You got some bad juju.
Oh well. Now, what if it didn't? What if your calculator decided to be ornery and not give you a decimal, give you the fraction?
Change it to a decimal.
Just put 1 over 1200 in the calculator, see what that decimal is, and see how they compare.
That's what I was saying.
Yeah. Okay. So there's a way around it. Okay. Questions? All right.